Physicist Sidney Coleman once said that the career of a young theoretical physicist consists of treating the harmonic oscillator in ever increasing levels of abstraction. To which I would like to respond with my own quote, with some hubris, that the life of an analyst consists of devising and applying the Cauchy-Schwarz, not Schwartz, no T, the Cauchy-Schwarz inequality and its daughter, the triangle inequality, to an ever-expanding set of mathematical objects. Here, analyst refers to those mathematicians who study real, complex, harmonic, functional analysis and related topics. Both statements are false in absolute terms, but there is an essential element of truth in both of them. The Cauchy-Schwarz comes in various guises, as we shall see in the fullness of time, and is typically introduced after the introduction of inner product spaces. However, the version for complex numbers can be presented without the machinery of the inner product spaces, and I shall take advantage of that to use its proof as a prop for the discussion of levels of mathematical intelligence. Its proof in the zeitgeist is typically furnished with appeals to either Pythagoras' theorem or to the analysis of a quadratic, but the version I shall present is purely algebraic, elementary algebra, following Rudin, whose iconic masterpiece, The Principles of Mathematical Analysis, third edition, 1976, is shown here. An inexpensive version of this book can be obtained from Amazon. Those of you who are theoretically inclined may want to get a copy of this book and look at sections 1.2 to 1.18 and 1.24 to 1.35 fields and the complex field. All of you are intimately familiar with at least two fields, the field of real numbers and the field of rationals. That notwithstanding, it may still be useful to take a look at these sections because one should look at the definition of a field and its properties in an abstract setting at least once. Next, we shall proceed and look at the proof of Cauchy-Schwarz using elementary algebra and use that as a prop for discussion of mathematical intelligence. The proof, the algebraic proof of the Cauchy-Schwarz for complex numbers following Rudin, who, though supremely elegant, is famously parsimonious, economy of explication being his trademark. And so, here and in what is to follow, I will often furnish missing conceptual jumps to aid comprehension. Two things before the proof. Number one, while the proof I am going to present is algebraic, the Cauchy-Schwarz has a geometric meaning, and we will come to that later. The second thing is that while the Cauchy-Schwarz is ubiquitous in mathematics and will be necessary for our purposes here as we traverse through manifolds, differential geometry, and measure theory, its inclusion here serves a different purpose. I would like to pick up a fragment from its proof as a seed for a brief discussion of intelligence, mathematical intelligence. Let's examine the statement of the theorem. N is a positive integer, and the AIs and BIs are complex numbers, I ranging from 1 to n. If AI is your complex number, then it is the sum of a real part, say x, and an imaginary part, say iy. Its conjugate, written with a bar on top, so AI bar, is itself with its imaginary part negated. And its modulus in the far right is defined as the non-negative square root of its product with its conjugate. If AI is a canonical complex number equal to x plus iy, then its product with its conjugate x minus iy is equal to x squared plus y squared, as you can easily verify taking into account that I squared is equal to -1. X squared plus y squared is patently real and non-negative. And this definition of the modulus makes sense, is good, provided the square root of x squared plus y squared exists. And so it does when x squared plus y squared is 0, guaranteed by the definitions and properties of fields in Rudin's section 1.12 to 1.18, where you can show that 0 times 0 is equal to 0, you can prove, and so 0 is a valid square root of 0. And so too it does when x squared plus y squared is positive by Rudin's elegant theorem 1.21, where he gives an existence proof of the nth roots of any positive real, not just square roots, nth roots, where n is any positive integer. Let's pause for a moment here. The case of x squared plus y squared 0, or the case of any real number being 0, is trivial, and let's set that aside. But it may seem whimsical or superfluous in 2025 to talk about the existence of square roots of positive reals several millennia after human beings have been working with square roots. That such square roots exist is guaranteed by quite subtle arguments of real analysis. And these are hard-fought gains over the last few hundred years, and poignant at this juncture in history when we are trying to teach machines how to understand and think. So, a renewed awareness of such subtle arguments from mathematics will help us design better machines, better AI. And so, I submit neither whimsical nor superfluous in 2025. Let's return to the proof. Here, I have defined uppercase A, B, and C in orange for the three sums in inequality 1. Observe that C does not include the modulus squared. It is just the quantity between the modulus symbols, so between the two vertical bars. A and B in the far right there are patently real and non-negative, being the sum of n terms, each of which is a modulus squared, AI modulus squared and BI modulus squared, so real and non-negative. So they are both real and non-negative. C, on the other hand, is in general complex, being the sum of n terms, each of which is in general complex, being the product of two complex numbers, AI and BI conjugate. Question: under what conditions is B equal to 0? Well, you can verify that B is 0 only when the BI's are zeros, in which case the BI conjugates are zeros, in which case the right-hand side of the inequality reduces to 0 because then it becomes A multiplied by 0. And so too does the left-hand side, because if the BI conjugates are zeros, then you have n terms, each of which is 0, AI multiplied by 0. So we have a trivial but true inequality, 0 less than equal to 0. Let's look at the more interesting case, B greater than 0. And under the assumption that B is greater than 0, let's examine this sum. The sum over J from 1 to n of Baj minus Cbj modulus squared. This sum, this expression, as we will find out, is the key that unlocks the proof of the theorem. And I shall return to it after I complete the proof of this theorem. This sum is patently real and non-negative, being the sum of n terms, each of which is a modulus squared, so real and non-negative. Applying the definition of the modulus squared, I multiply the quantity with its conjugate and arrive at this step where I carry out the conjugation. The conjugate of a sum is the sum of the conjugates of its operands, and the conjugate of a product is the product of the conjugates of its operands, guaranteed by sections 1.24 to 1.35, fields, complex fields and their properties in Rudin. Question: why doesn't B have a bar on top? Well, B, as we have already established, is a real number. And conjugation for a real number is an identity map, meaning that if you conjugate a real number, you get the same number back. So that's why B doesn't have a bar on top. In this step here, I carry out the multiplication inside the sum to arrive at these 4 terms. Each of these terms is a nested sum. And one way to verify that you get from this step to this step is to open out the sums. And you will find that this is what it simplifies to, which looks quite a bit simple. 3 of these 4 terms are similar to each other, 2 of them identical, one of them is a negative of the other 2. So minus BC modulus squared minus BC modulus squared plus BC modulus squared. This simplification is orchestrated by the specific choice of the starting point. As I mentioned, this is the key that unlocks the proof of the theorem. And in this next step here, we collect the terms. 2 negatives, 1 positive, B modulus C squared gives us 1 negative B modulus C squared. And then we have the remaining term B squared A at the front. We factor out B from both those quantities and observe that we have arrived at this step through a series of identities starting from a quantity which was non-negative. So obviously then this 2 must be non-negative. So that's why we have the greater than equal to 0. And since we are under the assumption that B is greater than 0, I can divide both sides of the inequality by B to get this last line after moving C modulus square to the right hand side. And voila, that is your proof of the Cauchy-Schwarz for complex number. This is exactly what we set out to prove, except that we have written it now here in inverted fashion. Instead of less than equal to, greater than equal to. Next will be a brief discussion of intelligence, mathematical intelligence, and we will use this key as the seed for the discussion.